Hey there, today we're going to talk about something extreme. It's the extreme value theorem. So, we've seen the extreme value theorem before as a function of one variable, and that says that if you have a function that's defined on some closed interval, you have a closed interval, then somewhere in this interval, the function attains its minimum, and somewhere in this interval, it attains its maximum. As long as the function is continuous and defined on the whole closed interval, then somewhere you have a max and somewhere you have a min. All right, so that works in higher dimensions too. Slightly different. So we have to have a function. All right, we've got a function. Hello, function. And now we want to talk about what's a closed interval here? Well, maybe we're not going to talk about a fully like an interval. We don't need it to be a rectangle. But let's say we have some set here. And what do we need about this set? We need that, just like in a closed interval includes its boundary. We need here our set to include its boundary. So we're going to call this a closed and bounded set. So it has to be closed, where it includes its boundary. And it's bounded in that it doesn't go off to infinity. So if I'm going to draw this a different way, maybe I would draw this in 2 dimensions. Right? In 2 dimensions, the way I would draw this is I would say, what does the domain look like? So the domain, what it can't be is it cannot be something that goes off to infinity. This is not allowed. So that's not allowed. And it can't be something where the boundary is open. And so boundary being open means that you're not including the boundary. So we've seen this type of thing before when you're talking about look at this set. We could talk about the set x squared plus y squared is less than 4. This set does not include its boundary when x squared plus y squared equals 4. So if we were going to draw that in the plane, we would probably draw a circle, but we would draw a dotted boundary just to represent that it's not including that. All right, so we're dealing with functions on closed and bounded sets. And so what this extreme value theorem says is that somewhere on this set, the function has a maximum, and somewhere on this set, you have a minimum. The absolute maximum, absolute minimum. What we were talking about last time, we were talking about these relative or local minima and maxima. And this time we're talking about when does a function actually, when are we guaranteed that a function has an absolute minimum or an absolute maximum? All right, so how do we find absolute extrema? So here's the basic thought. We're going to look on the inside of the function for critical points on the interior, and then we're going to find extreme values on the boundary. So how do we approach that? So we already know how to look for interior critical points. You find all critical points. Which one of those are inside the set that we care about, our closed and bounded set? You evaluate the function there. Then we look at the boundary. And because this is some nice set, then this set has a one-dimensional boundary. And so if you parameterize this boundary and you say, hey, we now have a function that goes along the boundary, Well, what's the function value along that? It ends up being a function value of the one parameter that's the boundary. And now you have a function of one variable, so you can find the critical points there. So you can say somewhere along here we had a min, somewhere along here we had a max, we had different critical points for different values of t. You evaluate the function there, and some endpoints, right? If you have a square, you might have to check the corners as well. But now we have a whole bunch of possible points where the maximum occurs, and a whole bunch of points where the minimum occurs. You find the largest and the smallest function values, so you can determine the absolute extrema on the set. All right, let's do an example. Find the global extrema of f of xy is equal to x squared minus 2xy plus 2y. It's extreme. And here we have a rectangle. X is less than or equal to 3, and y is less than or equal to 2. All right, so the first step is always to draw a picture. Always. Just draw a picture to help us out. So what do we have? We have x is between 0 and 3. Y is between 0 and 2. This is our domain. All right, and so our strategy is look for places that have critical points that are on the interior, and then we're going to check the boundary. So on the interior, how do you find critical points? You take the partial derivatives, you set them equal to 0. So f sub x, take the derivative 2x minus 2y, and the derivative with respect to y, minus 2x plus 2. So we now need to solve this. What do we get? We get 2x is equal to 2y, and we get 2x is equal to 2. So this is telling us that 1, 1 is critical, and that is in our domain. All right, so we're going to keep that one around. Keep around 1, 1, because that's a critical point that's on the interior of our domain that we care about. All right, so now we need to find the extreme values along the boundary. So we have 4 bits of this boundary. Let's look at them. So the 4 bits. Let's do the first bit of this. So what do we say? We have 0 to 3, 0 to 2. So let's do this part of the boundary where we let y be equal to 0. So we're only going to care about this part of the boundary from 0 to 3. And so we're going to look and see this. How do we parameterize this curve? We parameterize this curve as all points of the form x comma 0, where x goes between 0 and 3. Right here, we're parameterizing this curve. In this case, it's just a line, so that makes our life easier. But we have that this is our function. X goes from 0 to 3. So what is f of x0? F of x0 is what happens when we plug in y equals 0, and we just get the function x squared. So x squared, where x goes from 0 to 3. So this is just a parabola from 0 to 3, and we can just use our understanding of parabolas. We can either take derivatives, find some critical points if you want to, or we can just say this is a parabola, and we know the minimum happens at 0, 0, and the maximum happens at 3, 0. Because this is the lowest point, this is the highest point in the parabola. 2 more points. Let's keep those aside. Let's look at this side, f of 3 comma y. So f of 3 comma y, we plug in, right, this is y goes from 0 to 2. So we plug in 3 comma y into here, and we get the equation 9 minus 4y, right? X squared, so x is equal to 3, so 9 minus 6y plus 2y is 9 minus 4y. So 9 minus 4y is a line, right? So y goes from 0 to 2. 9 minus 4y, we have a point at 3 comma 2 and a point at 3 comma 0. So the maximum occurs here and the min occurs there. What about 0y? So on this edge, what do we get? If we plug in x equals 0, we get 0, 0, we get 2y. And now that's a line that is increasing, so the minimum occurs at the initial point, here at 0, 0, and the function then increases up to here, so 0, 2. So we're just chugging along. We've now looked at 3 different sides of this function, and we've checked out the interior. What's left is to look at this last side. And it's the most interesting one. So let's take a look at it. So we're plugging in x and 2. So into this equation, y is equal to 2, we get x squared minus 2, so 4x plus 4. So x squared minus 4x plus 4. And that is, so x squared minus 4x plus 4, that is equal to x minus 2 squared. So now we have a parabola. And the lowest point on this parabola happens at 2. So when we're at the point 2, 2, we have a minimum, and then we have to check the 2 boundaries as well. So we'll put those in our list. 0, 2, and 3, 2. So now we have a whole bunch of points. We have the point 1, 1. We have all the corners of the region, 0, 0, 0, 3, 0, 3, 3, 0, 0, 2, and 3, 2. But we also have this point 2, 2. And all of those are the points we have to test. We'll test each of those points and see what the function value is at each of those points and use those to figure out what the largest and the smallest on the whole region is. All right, so we're lining them up and we'll do them all. So we have to plug in 1, 1. When we plug in 1, 1, what do we get? We get 1 minus 2 plus 2, so 1. When we plug in 0, 0, we get 0. When we plug in 3, 0, we get 9 plus 0 plus 0. We get 9. When we plug in 0, 2, what do we get? 0 minus 8 plus 9. 0 minus 0 plus 2 is 4. When we plug in 2, 2, we get 4 minus 8 plus 4, we get 0. And when we plug in 3, 2, what do we get? We get 3, so 9 minus 2 times 3 times 2 minus 12 plus 4, which is 1. Okay, so what does that tell us? What that tells us is that the minimum values occur at 0, 0, at 2, 2. Those are the 2 places where the function value is as low as possible. And the highest value occurs at 3, 0. That's where the maximum is. All right, so stepping back, what did we do? We needed to find the extreme values on this set. To do that, we look for the points that are critical points on the interior, and we look for critical points really on the boundary as well. And we then take the set of all of those and find the largest and the smallest. All right, so let's stop there, and we'll use these techniques to talk about more word problem like optimization problems next. Ciao.